tangent squared. No. If I made tangent squared secant squared minus 1, then I can integrate it. How about we do that first? So let's replace tangent squared with secant squared minus 1. And make this as two integrals. T times secant squared minus the integral of t. Is that okay? And now, I don't think we have anybody sitting in the classroom next door to you. This is a very small crowd. Where's all my peoples? No peoples today. We're going to do this one by parts. I'm going to take that to be dv. And take t to be u. So that du is dt. And what was the integral of secant squared? Tangent. Okay, and so we have for that first integral uv minus the integral of v du. So uv gives us a t times the tangent of t minus the integral of v. V is the tangent of t. Du is dt. And let's not forget this integral out here. Let's go ahead and integrate that t right there and write that as minus 1/2 t squared. Okay, we're done because we have an integral formula for the tangent of t. There you go. So our final answer is t times the tangent of t. The negative natural log of cosine is going to change the sign to plus. The natural log of the absolute value of the cosine of t. And then minus the 1/2 t squared. So I didn't think to try it using the tangent as u, or the tangent squared as u. I didn't know if that would work. I don't think it will. Because the polynomial gets higher in degree. Who's got another one? You guys at home have one? Just type in your question. We're all good? Okay. Sorry, I missed that. Oh. Okay. Yeah. I don't see any kind of UDU substitution going on here. So I think what do we want to try? Yeah, the trig substitution. We do a trig substitution and because that 3/2 is a radical sign. So the variable squared is behind the minus sign. We'll take a sign to be that variable, and the a squared is 1. So I have x is sine of theta. Which makes dx a cosine of theta d theta. Okay. Let's see if any of these has any more juice in it. So let's start. What number is this one? 13. Okay, so let's fill that in up here. I'm going to go ahead and take the -3 out front because it doesn't look like it's going to cancel with anything. So 1 minus x squared is going to be 1 minus sine squared. All to the 3/2 power. And the dx has a cosine of theta times a d theta. Then we're going to replace 1 minus sine squared with cosine squared. So I have a cosine squared to the 3/2 power. When you raise the power to a power, you multiply exponents. So that's going to leave us with a cosine cubed on the bottom. Or we get 1 over cosine squared. Any suggestions on how to handle the integral of 1 over cosine squared? Make it a secant squared. That's right. And we know the integral of secant squared, right? That's a tangent. So all I'm going to do is get the tangent back in terms of x. X is the sine of theta. So if I just put an angle theta here, a ratio that reduces to x in terms of opposite over hypotenuse, puts an x here and a 1 there. And then leg squared plus leg squared is hypotenuse squared. So 1 squared minus x squared is the adjacent side. Tangent is opposite over adjacent. And so this is -3. Opposite is x. Adjacent is the square root of 1 minus x squared. Let's see. And that's a -3. Yes, sir.
Could you also do something weird with like make it opposite x squared to the hypotenuse x? I mean,
Oh,
it might
sure.
not be helpful.
Sure. Sure. Any ratio that reduces to x. Should it all be squared? Where? No, because we got an integral of secant squared is just a tangent to the first. Okay. More? Anybody need one of these for their apartment? Not that I know what it is. It's a thing where you can put other things in it. Not on it. Why it's here, I don't know, because I don't see where this thing could have come from. Maybe somebody brought it to class and forgot it. We might have to leave it here because they left their water as well. Is that it? Is that it? Is that all? Now you expect me to have something to do? Okay. Okay. Here's what I've got to do. We're going to look at types of integrals called I got them all worked out on Blackboard.
Okay.
I'm tired of integrating. Now I'm going to get you caught up with your other class, with my other class. I thought we did. How far did we get?
You're on.
Oh, that's okay. Look at the solutions on Blackboard. Section 7.7, we're looking at something called improper integrals. So what I want you to do is draw me the graph of y is equal to 1 over x squared. And we're going to find the area between that graph y is equal to 1 over x squared above the x-axis. To the right of the line x is equal to 1. So you're drawing me that graph and it looks like what? The graph of 1 over x squared. Kind of a hyperbola, not quite a parabola. As x gets large, 1 over x squared gets small. Not going to hit the y-axis, it's not going to hit the x-axis. You put the bottom by the x-axis, and then the vertical line x is equal to 1. And we're looking for that area right there. You think, well, you didn't give me from x is what to what? Well, I want it from x is 1 to forever, down the line. X is 1 to infinity. You think, well, that's a region that's unbounded. It's infinite. So how could there be area there that's not an infinite number? Well, this is an example of a function that bounds finite area, even though it's unbounded itself. So we compute area by computing a definite integral of the top graph minus bottom graph from left endpoint to right endpoint. So here's what we're going to have to compute is the integral from 1 to infinity of 1 over x squared dx. That infinity symbol makes it an improper integral. When one of the limits of integration is either plus infinity or minus infinity, or it's possible to have both limits of the integration be infinite, from minus infinity to plus infinity. Whenever you have that kind of situation, you've got an improper integral of type 1. I'll write that down in a minute. I'm going to show you how to do it first. The fundamental theorem of calculus says that if you have a continuous function on a closed interval, you find the antiderivative and plug in the two endpoints. So we're going to just make this a closed interval first. I'm going to put an arbitrary line over here, closing this off. And I'm going to say closing it off at some number x is equal to n. And I'm going to rewrite that as the integral from 1 to n. That allows me to compute this using the fundamental theorem of calculus. Then I'm going to move n. After I get this antiderivative evaluated, I'm going to slide n to infinity. That's how we'll handle these improper integrals of type 1. Stick a letter there, calculate the antiderivative, and then take the limit. How do you integrate 1 over x squared? Do that in your head or in the margin of your paper, or negative 1 over x. So I got to take the negative 1 over x, evaluate it from 1 to n, and then run the limit as n goes to infinity. So my antiderivative evaluate both endpoints gives me a negative 1 over n minus negative 1 over 1, which is plus 1. Well, what happens to 1 over n when n gets infinitely large? It goes to 0. So as n gets large, negative 1 over something large essentially becomes 0. And we have not only finite area, we have exactly 1 square unit of area under that curve. Isn't that cool? Now, sometimes when we try to do this same kind of deal, we're going to get something that doesn't have a finite area. Let's make a minor modification. This is the graph of y is equal to 1 over x squared. The graph of y is equal to 1 over x looks almost identical to that. It passed through, both of them pass through 1, 1. But 1 over x is a little bit taller. They'll pass at the same point at 1, 1. But 1 over x, it'll look something more like that, the blue one. Tighter to the y-axis, but wider away from the x-axis. Let's do the same thing. Let's attempt to find the area between y is equal to 1 over x, the x-axis to the right of x is equal to 1. Find the area underneath the graph of y is equal to 1 over x to the right of the line x is equal to 1. So we do the first 2 steps the same way. We write it as the integral from 1 to infinity, then we stick a letter up there where the infinity symbol is, and let that limit, take that letter to infinity. Okay, so this little maneuver here, even though it looks like it's just a waste of writing, is what allows us to use the fundamental theorem of calculus. Find the antiderivative, evaluate it at top minus bottom. What's the antiderivative? The natural log. So I'm going to have the natural log of n minus the natural log of 1, and then I take the limit as n goes to infinity. What's the natural log of 1?
0.
That's 0. What do you think happens to the natural log of n when n goes to infinity? It does go to infinity. A logarithm is a growing function. So even though it grows slowly, here's the graph of the natural log of x. Even though it grows slowly, if I keep going out this way, the y values keep getting bigger and bigger and bigger. So this particular area is infinitely large. When the improper integral takes on a value of either infinity or minus infinity, or if it doesn't exist for some reason other than that, then we say that this integral diverges. And it's because the graph of 1 over x doesn't hug the x-axis tightly enough. So I'm going to write down what I mean by the improper integral of type 1, and then I want you to think about how large or small or whatever, what size power will be here so that it does have finite area. Is it numbers 2 and larger? Or can I pick a number between 1 and 2 and it'll still have finite area? What's the smallest number that I could put here so that 1 over x to that power has finite area? Greater than 1 because?
If it's 1, then it's
If it's 1, it's a logarithm. If it's slightly bigger than 1, then we use the power rule, right? So if I have something like an x to a power down here, and that's a number slightly bigger than 1, I would integrate it by writing it as x2 minus the power. And in this step, I would have x to minus the power plus 1 divided by that. If this number is bigger than 1, then minus p is bigger than 1. Is bigger than 0. Okay, let's see it again. P is bigger than 1. So minus p, when I add 1 to it, it'll still be negative, which will allow me to put in the denominator. And that's what we need, that term to be able to go in the denominator when I evaluate it at n. So that's exactly right. The integral from 1 to infinity of 1 over x to the p dx converges for values of p bigger than 1. It diverges for p 1 or smaller. So if I want to integrate 1 over the square root of x from 1 to infinity, it should diverge. But 1 over x to the 1.1 will converge. Not to 1, but it'll hit something, right? So a type 1 improper integral has the form of either the integral from some number to infinity of a continuous function, or minus infinity to another number, or even minus infinity to positive infinity. If we have this form, then we rewrite the problem with the limit as n goes to infinity. And we integrate from a to n. Here we'll put a number, a letter at the bottom, and let that letter go to minus infinity. So I'll just use an m. And I'm integrating from m to b. If we have this case, we've got to do 2 integrals. We first break this up at some in-between point. I usually use 0, and write this as the integral from minus infinity to 0 plus the infinity, from the integral from 0 to infinity. And then we do these 2 cases here and here. If any one of these limits is infinite, then we say that the indefinite or the improper integral diverges. If these limits exist and at some finite number, then the integral converges to that number. So what we need to happen for these integrals to converge is that our antiderivatives have to have some sort of asymptotic behavior. Or even the integrand has to have some sort of asymptotic behavior. So let me see if I can think of some examples of things that we can integrate that will converge or diverge. Nope, can't think of any. This class is over.
If the integral, like the area, ends up being a rational number, that considered
Irrational number like pi, pi is a big number. So any number in the world, any number in the world, you make that convergent. Otherwise, if it's infinite, then it's divergent. Okay, so it could diverge to infinity, it could diverge to minus infinity, it could diverge because it doesn't exist. So how about we look at something other than a 1 over x to a power? Let's look at so the instructions from here on out is determine whether the improper integral converges or diverges. If it converges, I want you to tell me what it converges to. If it diverges, does it diverge to plus infinity or to minus infinity, or for whatever reason you're going to tell me? substitute the improper integral from 0 to infinity of e to the negative 5x dx. By first writing it as the appropriate limit. We're going to replace the infinity symbol up above, so n is going to go to infinity. And we're going to integrate from 0 to big N, e to the negative 5x dx. So what's the integral of e to the negative 5x? Negative 1/5 e to the negative 5x. Then we have to evaluate that from 0 to big N, and then take the limit as big N goes to infinity. Put those values in there, and the expression that I need to look at is negative 1/5 e to the negative 5n minus a negative 1/5 gives me a plus 1/5 e to the 0. Let's e to the 0. So I'll just leave it at 1/5 right there. The fact that that exponent is negative means essentially that that's e to the 5n in the denominator, right? Maybe that helps you evaluate the limit better. Five n. Can you tell me what happens to that expression in front as n goes to infinity? It goes to 0 fast, doesn't it? E to the 5n grows real fast. This goes to 0. So this thing converges to 1/5. Where did all my examples go? All right, let's do one more. No, because that goes to 0, and then when I subtract, that becomes a plus. Okay. All right, let's try that one. The integral from 0 to infinity of the natural log of the cosine of x dx. So we just mechanically fix the problem. And then cross our fingers and hope we can find the antiderivative here. Help me. How do you normally integrate logarithms? Try use of. Use cosine. It's not going to work. by parts. Integration by parts. Where you're forced to pick u to be the natural log of cosine of x. And pick dv to be dx. All right, help me out. What's the derivative of the natural log of the cosine of x? Whatever cosine times minus the sine. Can I write that as minus the tangent? All right, and v is x. Oh, goodness. Okay, so we've got uv minus the integral of v du. uv is going to be x, natural log of cosine of x. uv minus the integral of v du. So I'm going to change this to a plus because my du has a negative. Oh God, who made this problem? Maybe I integrate by parts again. I also need to have this one. Okay, let's try it. We're going to do integration by parts again. So u is equal to, you said tangent or dv? You want u to be x, dv to be the tangent. So du is dx, v is okay. Oh, goodness. Who made this example up? So this is from the last one. We're going to assume that we're looking only where cosine's positive. I guess that's a bad assumption. That should probably be an absolute value bars, right? Because we can't take the log of a negative number. So that's an absolute value. Okay, plus uv, but v has a minus. So minus x, natural log of the cosine of x. Minus the integral of v, but the v has a minus. Let's make that plus. Natural log of the cosine of x dx. That's not circular, is it? It didn't. Yep, I probably can't do this integral. How else would we do it? Right, it would be circular if this were a minus sign, but I got a plus. That stinks out loud. Learn how to integrate natural log of cosine of x. Well, I can tell you how not to integrate it. I thought I could do this in my head. uv minus the integral of v du. Yeah, that's the plus sign. X. Okay, so what if u is tangent? Du is secant squared. V is x. Let's try that. I don't know if this doesn't work, then we punt. Says that? Bummer. All right. Okay, so it wasn't, that's not a good example. I was trying to find something that diverged. Well, not only do we not know, we can't integrate this SOV. Which is kind of a good point because we spent how many weeks now learning how to integrate more things, and there's still things that we can't integrate. That's right. So there are numerical schemes to do those kinds of things. Things called the Trapezoidal Rule and Simpson's Rule. And so in practice, when you're doing your engineering, you just plug it into this package integrator, but it's using one of those integration schemes. Okay, so pretend that didn't happen. That's 3.5 minutes of your life that you're not going to get back. It's a lesson. Sorry? Simpson's rule is a numerical method to find a value of a definite integral that you can't compute, like this one in closed form. It's a version of a Riemann sum, but it uses, well, the trapezoidal rule, instead of uses rectangles, uses trapezoids. Simpson's rule averages endpoints. So it kind of, it's a version of an average. So it's just something that's supposed to converge faster. Well, I wanted one that's not going to converge. Here, let's try this. You guys wanted an integration by parts. Let's try this one. This one works with integration by parts, but it's actually going to converge, I believe. It's actually one of your Wedworth problems. So I was hoping to do an integration by parts that wasn't your Wedworth problem, but as you can see, I wasn't terribly ready for that. Okay, so this time we put a letter at the lower endpoint and take that letter to minus infinity. But the product with x and e to the x is an integration by parts problem, where u is x and dv is e to the x. Du is dx, and the integral of e to the x is e to the x. So we're going to take the limit as m goes to minus infinity. And so we've got u times v, x e to the x. That has to be evaluated from m to 0, minus the integral of v times du. And that's going to be evaluated from m to 0. Okay, but again, the integral of e to the x is e to the x. So let me write this like this. I'm going to get an e to the x here. I have an e to the x there. So why don't I factor it out and write this as x minus 1 times e to the x. From m to 0. Okay with everybody? It'll help me take the limit if I've got things written as a product as opposed to a difference. Okay, we'll put the 0 in for each x first. And then we'll put the m in. When x is 0, I have -1 times e to the 0. E to the 0 is 1, so we just get -1. Now I subtract that. X minus 1, oops, not an x, I want an m minus 1. Times e to the m. So this one doesn't matter. I'm really worried about, let me do it even this way. Let's see, I'm pulling this limit into here. Okay. Now m is going to minus infinity. So when I subtract 1, this first term still goes to minus infinity. What about the second term? What's e to the minus infinity? It's 0 again, because that means it's in the denominator. Infinity times 0, whether it's plus infinity or minus infinity, is an indeterminate form. It means, I don't know. But we can fix it so that we can use L'Hopital's rule. Who remembers L'Hopital's rule? L'Hopital's rule says that if you have a limit that takes on the form of either 0 divided by 0 or infinity divided by infinity, then we take that limit by taking the limit of the ratio of the derivatives. If that expression has a limit, then so does that. So what we got to do is make an adjustment to this so that it has the form of either infinity over infinity or 0 over 0. Remember doing that in your Cal 1 class? You guys that were in my class pretended to remember. Something like that. We take one of the terms and put it in the denominator. And to me, the easiest one to move is the e, because all you do is change the sign on the power. So I'm going to rewrite this. Here's the -1 from the antiderivative. Here's the minus sign, and now my limit as m goes to minus infinity. And I'm going to keep the m -1 up here, put the e on the bottom by changing the sign of the power. And now as m goes to minus infinity, the numerator goes to minus infinity, the denominator goes to e to the positive infinity, which is at infinity. So it behaves like minus infinity over infinity. The sign doesn't matter. Infinity over infinity allows us to use L'Hopital's rule. Take the derivative of the top, divide it by the derivative of the bottom, and then see if you can take the limit. Keep in mind that this -1 here and minus there, and here goes L'Hopital's rule. The derivative of the top is just 1. What's the derivative of the bottom? Derivative? Negative e to the negative m. And now m goes to minus infinity. So this makes it plus infinity. E to the positive infinity gets large. Divide that into 1, and that goes to 0. So this behaves like 1 over infinity. And so our original integral takes a value of -1. Okay. So sometimes you'll have to pull out L'Hopital's rule from wherever you're storing it. I guess I need to show you the type 2 improper integral. Okay, so here's a type 2 improper integral. What do you think makes this improper? It's pretty reasonable to me. Yeah, the integrand has an x -1 in the denominator, and 1 is an x value that makes my denominator 0. A type 2 improper integral is one that has an integrand that becomes infinite at either the lower limit or the upper limit or at some point in between. type 2 improper integral. We've got the integral from a to b of f of x dx, and then either f is infinite at either a or at b or at some point between a and b. As with the ones with the infinite limits of integration, sometimes these integrals converge, sometimes they diverge. And we kind of integrate them in the same way. In this example, this was our point of discontinuity. So what we do is we pick some letter and let it live near that number. I'll use an A. Compute the antiderivative as a function of A, and then we take the limit as A, in this case, goes to 1. And it's coming to 1 from the interval from 1 to 5, so it's coming to 1 from the right. So we're computing a one-sided limit here. So now that function is continuous at all numbers between A and 5, I can integrate it. We integrate it as a u to the -1/2, right? Use x minus 1 to use dx. What's the integral of u to the -1/2? 2 u to the 1/2. So this integral looks like 2 times my u under the radical sign. So now I put in the top limit and the lower limit. Like that. So the square root of 5 minus 1 is just 2. 2 times 2 gives me 4. What about the limit as a goes to 1 from the right of this expression over here? What happens to it as a goes to 1? Gives me 0, 1 minus 1, right? So this is an example of an integral that converges, and it converges to 4. Okay? So again, this is going to be some sort of vertical asymptote. We need the function in here to get close enough to the vertical asymptote to essentially seal off an area. If I change my problem slightly to that, when I integrate that, I'm still going to have an x minus 1 in the denominator, right? That makes this power of 2. And if there I've got an x minus 1 in the denominator, when I do this limit, it's going to have a 0 downstairs. So that's an example of something that will not converge. Okay, so I'll go more into detail about that on Monday. Everybody good at home? All right, I'm cutting you off now, unless you have any questions.